Determining a unique antiderivative. Okay, so let's move on to understanding how we pinpoint a specific antiderivative. Now, remember in the sections we just covered, we learned that when we find the indefinite integral of a function, that is, we antidifferentiate, we don't get just one answer. Instead, we get a whole family of functions. This family is represented by what we call the general solution, written as f of x plus c. Think of f of this x as a function that, when differentiated, gives you the original function you started with, and c is the constant of integration. Now here's a crucial point. The derivative of any constant, any value like 2, minus 5, or even pi, is always 0. What that means is that if you add different constants to the same function, you don't change its derivative. Therefore, infinitely many functions can actually share the same derivative. However, in many real-world problems and in more advanced mathematics, we don't want just any function that has the correct derivative. We need one specific function. That's where the concept of a unique antiderivative, also known as a particular solution, comes in. We'll be learning how to take that family of functions, f of x plus c, and narrow it down to just one by using some extra information. In the following slides, we'll see exactly how to do that. Understanding the concept. Okay, so let's move on to slide 2. As we discussed on the previous slide, when we find an antiderivative, we actually get a family of functions, all differing by a constant. Remember, that constant c is the key. Now the question is, how do we pinpoint one specific function from that family? That's what this slide addresses. To move from that general solution, that family of curves, to a unique, specific solution, we need some extra information. Think of it like needing a clue to solve a puzzle. This extra information usually comes in the form of what we call an initial condition or a boundary condition. These both serve the same purpose, but you'll encounter different terminology depending on the context. Let's focus on initial conditions for now. An initial condition is simply a known point that the original function must pass through. We represent this point as an ordered pair, written as x sub 0, y sub 0. That means we know a specific x value and the corresponding y value that the function must have at that x value. Mathematically, this means that when x is equal to x sub 0, that specific x value from our known point, the value of our general solution, which is f of x plus c, must equal y sub 0, the y value from our known point. Let me say that again to make it clear. If we plug x sub 0 into our function f of x plus c, the result has to be y sub 0. This gives us an equation we can solve. Because we know x sub 0 and y sub 0, and we have an expression for f of x, we can substitute those values into our general solution and then solve for the unknown constant. See, once we find the value of c, we've uniquely defined our antiderivative. We've moved from a family of functions to a single, specific function. This is a crucial step, and we'll see how it works in practice on the next slide with a concrete example. So, keep this concept of using an initial condition to solve for c firmly in mind. Step-by-step procedure to find a unique antiderivative. Okay, so now that we understand why we need to find a unique antiderivative, remembering that an indefinite integral gives us a family of functions, and we need extra information to pinpoint just one, let's look at the how. This slide outlines the step-by-step procedure to actually find that unique solution, also known as the particular solution. Step 1, find the general integral. This is where we start with the derivative, let's call it f of x, and we perform integration. Remember, integration is the reverse process of differentiation. When we integrate f of x, we obtain the general solution, which we represent as f of x plus c. Don't forget that plus c is crucial, as it represents the constant of integration, acknowledging that infinitely many functions can have the same derivative. Step 2, substitute the given point. Now, this is where the initial condition comes into play. We're given a specific point, usually denoted as x sub 0, y sub 0. This tells us a specific x and y value that our function must satisfy. We take those coordinates and plug them into our general solution, f of x plus c specifically, we replace every instance of x in the equation with the x sub 0 value, and we set the entire result of the function equal to the y sub 0 value. Step 3. Solve for c after substituting. We'll have an equation with c as the only unknown. This step involves using basic algebra to isolate and solve for the numerical value of c. It's just a matter of rearranging the equation to get c by itself on one side. Step 4. Write the particular solution. Finally, once we've found the value of c, we substitute it back into our general solution, f of x plus c. This gives us the particular solution, a single, unique function that satisfies both the derivative and the initial condition. This is the function we're looking for. Keep in mind, we'll see this process in action on the next slide with a concrete example, and then again with a physics application. Also, we'll cover common mistakes to avoid later, so you can be confident in your calculations. Mathematical example. This slide presents a problem. We need to find the unique antiderivative of the function f prime of x, which is equal to 3x squared plus 4x, and it must pass through the point 1, 6. Remember, this point gives us the specific information we need to pinpoint one function from the infinite family of antiderivatives. Step 1. Find the general integral. Here, we're going to perform the integration. We have the integral of 3x squared plus 4x with respect to x. We can split this up into two separate integrals. 3 times the integral of x squared dx plus 4 times the integral of x dx. Now, let's integrate each term. The integral of x squared is x cubed over 3, and the integral of x is x squared over 2. So we have 3 multiplied by x cubed over 3, plus 4 multiplied by x squared over 2, and don't forget the constant of integration. See, simplifying this, the 3's cancel out in the first term, and the 4 divided by 2 simplifies to 2 in the second term, giving us x cubed plus 2x squared plus c. This, as we know, is our general solution, the family of all possible antiderivatives. Step 2. Substitute the given point 1, 6. Now, we'll use the initial condition to find the specific value of c. The point 1, 6 tells us that when x is equal to 1, the value of our function f of x must be equal to 6. So, we substitute x equals 1 into our general solution. This gives us 6 equals 1 cubed plus 2 times 1 squared plus c. Step 3. Solve for c. Let's simplify this equation. 1 cubed is 1 and 2 times 1 squared is 2. So we have 6 equals 1 plus 2 plus c, which simplifies to 6 equals 3 plus c. To isolate c, we subtract 3 from both sides of the equation, giving us c equals 6 minus 3, which equals 3. So, we've found the value of our constant of integration. Step 4. Write the particular solution. Finally, we substitute the value of c, which is 3, back into our general solution. This gives us f of x equals x cubed plus 2x squared plus 3. This is our unique antiderivative or particular solution. It's the one function that satisfies both the derivative condition, f prime of x equals 3x squared plus 4x, and the initial condition, passing through the point 1, 6. Okay, let's work through a concrete example to solidify our understanding of finding a unique antiderivative. As we discussed in the previous slides, we often start with a general solution, a family of curves, and then narrow it down to a specific curve using an initial condition. Remember, this process is crucial not just in mathematics, but also in applications like physics, as we'll see on the next slide. We'll explore how this concept applies to finding the position of an object given its velocity and initial position. Real-world application, physics kinematics. Now, in physics, a fundamental relationship exists between an object's position and its velocity. Remember that velocity is the rate of change of position with respect to time. Mathematically, this means velocity is the derivative of position. Conversely, position is the antiderivative, or the integral, of velocity. So, if we know the velocity function and the object's starting position, we can determine its position at any given time. Let's look at the scenario presented here. We have a particle moving along a straight line, and its velocity is given by the function v of t, which is equal to 2t plus 5 meters per second. We also know that at time t equals 0, the particle is at a position of 10 meters. Our task is to find the position function, which we'll denote as s of t. Step 1. Find the general position function. To do this, we need to integrate the velocity function. So s of t is equal to the integral of v of t, which is the integral of 2t plus 5 with respect to t performing this integration. We get t squared plus 5t plus c. Remember, we always include the constant of integration, c, when finding an indefinite integral. That's our general solution. Step 2. Use the initial condition. Now, this is where we move from the general solution to a unique one. We're given that the particle is at a position of 10 meters when time is 0. This gives us a specific point, 0, 10. We substitute these values into our general solution. So, we have 10 equals 0 squared plus 5 times 0 plus c. Step 3. Solve for c. Simplifying the equation, we get 10 equals 0 plus c, which further simplifies to 10 equals c. Therefore, the value of our constant, c, is 10. Step 4. Final position function. Finally, we substitute the value of c back into our general solution. This gives us the unique position function, s of t equals t squared plus 5t plus 10. This function now tells us the exact position of the particle at any time t. Okay, so let's move on to a real-world application of what we've just learned about unique antiderivatives. As we discussed in the previous slides, finding a unique antiderivative requires an initial condition. This slide shows us how that plays out in a physics problem. This example beautifully illustrates how initial conditions allow us to pinpoint a specific antiderivative from the infinite family of possible solutions. We'll be looking at common mistakes in the next slide, so make sure you understand this process before we move on. Common mistakes to avoid. First, it says omitting the constant c. Now, this is huge. A very frequent mistake is forgetting to add plus c after you perform the integration. Remember, when we find the indefinite integral, the general antiderivative, we always add that constant of integration, c, because the derivative of any constant is 0. So, infinitely many functions can have the same derivative. If you leave out the plus c, initially, you've lost the ability to solve for it using the given point, and you won't be able to find that unique antiderivative we're looking for. It's like trying to build a house without a foundation. It just won't stand up. Next, we have incorrect substitution. This refers to how you plug in the values from your initial condition into the general solution. It's crucial to remember that the y value, which represents the function value at a specific x, needs to be on one side of the equation. And, of course, you need to substitute the x-coordinate of your point into the variable x within the function itself. Don't swap them around. Think of it like matching pieces of a puzzle. They need to go in the correct spots. Finally, sign errors. This is a simple algebra mistake, but it happens a lot. When you're isolating c to solve for its value, be extremely careful with your signs. The example given is a good one. If you have the equation 5 equals 8 plus c, then c is equal to -3, not 13. A lot of students will incorrectly add instead of subtract, or vice versa. Always double-check your arithmetic, especially when dealing with positive and negative numbers. Okay, let's move on to slide 6. This slide highlights some common mistakes students make when determining a unique antiderivative, and it's really important we address these before you tackle more complex problems. Remember, we've just gone through how to find a general solution and then refine it into a specific, unique solution using an initial condition. Avoiding these 3 mistakes will significantly improve your accuracy and confidence when finding unique antiderivatives. And remember, we'll wrap everything up on the next slide with a quick review of the key takeaways. Key takeaways. First, let's remember the general solution. This refers to the family of all possible antiderivatives of a function. When we perform indefinite integration, we always get a plus c at the end, right? That c represents any constant, so the general solution is written as f of x plus c, where f of x is some function and c is an arbitrary constant. Think of it as an infinite number of curves, all with the same shape but shifted up or down. Now, we often don't want just any antiderivative, we want a specific one. That brings us to the particular solution. This is the one unique antiderivative that satisfies a specific condition that's given to us. It's like picking out one specific curve from that whole family of curves. To actually find that specific curve, we need some extra information, and that's where the initial condition comes in. An initial condition is simply a known point on the function, a pair of values, usually written as x sub 0, y sub 0. This tells us that when x is equal to x sub 0, the function's value must be y sub 0. This single piece of information allows us to solve for c and pinpoint that unique antiderivative. Finally, let's quickly run through the process we follow to find this particular solution. It's a four-step process. First, we integrate the given derivative to find the general solution. Then, we substitute point, meaning we plug the x and y values from our initial condition into the general solution. Next, we solve for c using basic algebra. And finally, we finalize function by plugging the value of c back into the general solution, giving us our particular solution. Okay, let's recap everything we've learned about finding unique antiderivatives. This is slide 7, and it's all about solidifying the key takeaways. So, remember these key ideas, and you'll be well equipped to tackle any problem involving finding unique antiderivatives. We've covered the theory, seen examples, and now have a clear process to follow. In the next problem, you'll be able to apply these concepts with confidence.